Mostly, we will describe our preliminary results achieved in this project, and in the end, I will also survey some of our future plans in the project relating to better sensor arrays for vapors and liquid compositions. So an overview of the talk. We'll first describe an outlook of why we're doing and developing our devices. Then we'll move on to one application that is gas sensing with resonant microstructures. And then we'll move on to the liquid sensors, a completely different environment that's viscous, so it demands different devices for liquid composition sensing. We'll describe this system, and in the end, we will conclude with the future geometries that we plan to apply in next generation devices. So why use micro and nano-opto-electromechanical systems for applications? Because as we know, there are many alternative technologies. So we claim that the motivation for fabricating and applying such devices is that they potentially combine wanted qualities. Basically, what you want in sensors is to have high sensitivity, fast response, low time constants, energy efficiency, and the low cost of fabrication. So, of course, some of these demands are contradictory to each other. You need some compromise many times. But we claim in this field of micro-opto-electromechanical systems, or MOEMS, and nano-opto-electromechanical systems, that we can combine all four wanted qualities and apply them in a multitude of applications, such as material sensors, on which I will concentrate today, an electronic nose application, also for imaging applications, and in high-speed photonic switches. So today I will mostly talk about this aspect of the group activity. In matter sensor applications, we are looking at gas and liquid ambient environments, and we know that these are opposite limits, right? In the biomedical and clinical applications, for example, in breath analysis and in olfactory-like sensors, we would like to get sensitivity to vapor concentrations of about 1 parts per million or below, right? On the other hand, if we're looking at public safety and security applications, we want to detect flammable, explosive, and abrasive devices. For example, TNT and C4 have a vapor pressure of less than parts per billion. So we have different requirements for different kinds of applications. And most importantly, we also want selectivity of our sensor to a specific analyte. And we don't want it to be overloaded with other stuff, for example, water vapor that is also existent in the air. So that is a big problem. Just to give you some indication, if we look at the breath composition of exhaled breath of a human, once water has been removed, of course, water is the highest element that exists in the exhaled breath. So if we look at this paper by the High Group from the Technion, we see that there are dozens of trace elements that exist in the breath, and some of them are related to disease. For example, cancer. So it's not a direct cause-effect, but it is some correlation. So some diagnosis can be made with breath analysis of healthy patients before they develop the disease. So if we look at the existing problem for gas analysis, the conventional lab tool for analytical chemistry is the gas chromatographer and mass spectrometer. GCMS. Basically, it's just an oven with a very long column that separates at high temperatures the different components of the gas and detects them as a function of time, these different elements. And if we want to really analyze a sample composition, we use this machine. Today's technologies are smaller than this. We have a rack of about 2 meters high in the gas chromatographer. Today, you can have them in a suitcase that weighs about 10 kilograms. But still, this is expensive, bulky, complicated to operate. You need a technician to operate them. And mostly, it's non-portable. So you still see gas chromatographers only in laboratory settings, not in everyday settings. You don't see them on your cell phones. People have tried several attempts to use mechanical elements to apply them as vapor sensors. For example, there was a company called VOC-check that existed until 2011. And they attempted to create this low-cost handheld multiplex gas vapor sensor. But we tried to operate it. It is reliable only when using highly flammable gases. For example, acetone and ethanol, things that are easy to sense anyway, that have a very high vapor pressure. But they are completely unreliable for trace vapors of TNT. So this product didn't really work out, and it relied on an all-electrically driven array of silicon cantilevers, an array of cantilevers that are operated through a Wheatstone bridge, right? 4 electrodes. So you excite the base, this edge of the cantilever, and the tip of the cantilever starts vibrating. On this gold pad, different chemicals have been deposited that have a different response to the ambient gas, and a multiplex detection of this 128 different elements was supposed to give a signature of different gases. So it didn't work with this kind of technology. In our application, we combine optical elements and optical drive rather than a thermal drive together with nano cantilevers that have a higher sensitivity for small changes. So first I would just like to survey the 2 schemes for sensing that are typically used with micro and nano-mechanical elements. One is the static mode, in which a material is adhered on the cantilever, and the tip is deflected statically. Once, if you shine a laser, for example, on this tip, you can measure the displacement. And if you functionalize your device with some, let's say, antibody, you can have a specific upwards or downward shifts that are proportional to the concentration of your analyte. So this is a deflection kind of a measurement in this cantilever, and it's done in real time to the edge. Another scheme for operation is the one that we employ, is the dynamic resonant mode, in which we actuate our device periodically at a given frequency, and we sweep the frequency of drive. So in a spectrum, we get a spectral response of this mechanical element. The amplitude is a function of the frequency. In our case, we measure the velocity of the tip as a function of the frequency. In the linear regime, we get the Lorentzian shape of the response. So if you have a sampling machine that's fast enough, you can measure these resonant curves in real time. Once you add a mass, let's say, to the tip of your resonator, the total mass is higher, and therefore there is a frequency shift downwards in the resonant response. So measuring the frequency shift in the spectral domain, you can find out what is the mass that has been deposited. So with nanoresonators, people have been able to measure single molecules single proteins, even single protons, if this kind of device is small enough, if the internal mass of the device is sufficiently small. But this is kind of a gravimetric mass sensor. It is not a chemical vapor sensor. Another possibility is that the stiffness of your device changes in reaction with your environment. If the cantilever becomes stiffer, you get a frequency shift upwards, right? So finding out the correlation between the stiffness change in your resonator that might be consistent of various different layers, in the frequency domain, you can monitor the frequency response as a function of time. So if we only have a mass loading effect on the frequency shift, we can find out what is the minimum mass that's being measured. Now, a big challenge in this kind of devices is the quality factor in ambient conditions. So the quality factor is just the central frequency of this Lorentzian divided by the width of the Lorentzian. And typically, there is a problem in nanoresonators. As we make them smaller and smaller, the frequency gets higher and higher. We get into the gigahertz regime. So we should get higher quality factors, but more dissipation occurs inside the film, in the material layer, and as a result, the quality factors get really, really bad, right? So it's kind of a trade-off, and the current study is actually reducing the clamping losses in arrays of nanoresonators so that the frequency response of the fundamental mode is high enough, and the quality factor remains high enough, so that we can achieve very high sensitivities. So in our previous work, we have applied micro-bridges that are doubly clamped, not cantilevers, but doubly clamped bridges that have been placed inside the flow chamber where we mix gases. So we know what kinds of gases we mix here between the reference channel that is just clear nitrogen and the analyte channel that goes through a bubbler. It mixes some of the vapor inside the flow chamber. This device is driven electrostatically, and most importantly, our bridge is composed of polycrystalline silicon that's coated with a polymer layer only on top of the bridge. So we have a monolayer of PMMA, right? That's not selectively, it's not selectively absorbs any specific kind of analyte, but it swells and changes its volume by up to 40%. Okay, so in our device that we analyzed previously, we're working with buckled bridges. There is a compressive total stress inside the bridge, and it is being stressed from both sides. And the stress is very close to the critical buckling stress. So when you apply compressive stress to your bridge, initially it stays flat, but at a certain point it becomes buckled, either upwards or downwards. Very close to this critical buckling stress, this critical point, you notice that the resonant frequency as a function of stress, it changes abruptly. It increases very fast, and the slope of this curve is theoretically infinite at this point. So theoretically, you have a very, very high sensitivity in the frequency domain in our devices. Our goal was to create maybe 128 of these kind of critically buckled beams, and to coat each one of them with a different selective polymer. So, of course, in our setup, we could only focus on one device, only on one bridge, because our sensing is optical, and we had to move on a translation stage among all the different elements in our array. right? So it's not really a real-time measurement. In the future, we will also make real-time measurements in arrays of such devices. This is the fabrication process in which we first deposit our film by thermal evaporation. Afterward, we define our device photolithographically and wet etch release the bridges. After release of the base bridges, we apply molecular vapor deposition of anti-adherent hydrophobic layer. So we need an hydrophobic layer intermittently before we add our swelling polymer of interest, because we do not want to get stiction of our basic resonator. In addition, we also wanted to spin coat. We want to add the adhesive polymer layer only on top of the bridge, not under the bridge. So when we finish depositing the FOTS film and expose our device to plasma etch, we get rid of the top hydrophobic layer. We have a hydrophobic layer only between the device and the substrate. And then we can just deposit the PMMA or any other polymer with the abrasive methods, right? We do not need to worry about stiction. So that was kind of our innovation here in the fabrication process. It's stage 3 and 4. I don't have much time left, but I will describe the results. So in our devices, we examined several kinds of bridges. Some of them are closer to critical buckling than others. And an estimation of the stress in this bridge is 72.6 megapascal, pretty close to the critical stress that was about 56 megapascals in this film. And indeed, we get larger frequency shifts as a function of the concentration. And we get a different response for each and every kind of analyte that we use, right? Because the swelling depends on the pressure of the gas. And the vapor pressure is different for each and every element. So in water, what we get is kind of a complicated curve, but there is a complicated diffusion relationship of PMMA with water. We actually expected this to happen. And indeed, the response is with the same kind of slope, but the dynamic range is lower when we use a highly buckled bridge that is very, very curved, far away from the critical stress. One of our future goals is actually to control the homogeneity of our film all throughout the process. So in the end, we get, if we start with a bunch of bridges that are close to critical buckling, they will stay there at the edge, and we can operate all of them at the same frequency span. And in the end, we also get kind of a recognition plot where we have two components for our measurement. One of them is the frequency shift per concentration change in the linear regime before saturation, and the other one is the time constant for swelling of the layer. Each analyte has a different time constant to saturate. And we indeed get in the recognition plot different areas corresponding to different materials. The problem here is that this is not a real detection. We have only 2 degrees of freedom, right? We have only one frequency shift and one time constant for each analyte. So we can't actually really get a clear and a complete signature of a certain component of our gas. It could be many other components. What we actually need is to make a real-time measurement that is a multi-component with at least 4 or 5 dimensions. And for that, we need 4 or 5 resonators that are analyzed at the same time. Over here. At higher concentrations, we just get saturation as a function of time of our frequency shifts upwards. You will notice that the shift is 200% larger than the base frequency here. So theoretically, a buckled bridge would have a resonance frequency of 0, right? But currently here we are pretty close to the critical buckling initially, and we get frequency shifts that are very substantial. In theory, we could get even larger frequency shifts. In the low concentration regime, it really is a linear response, and it extrapolates to 0. I remind you that in security hazard applications, we actually need to work with the very low concentrations below the 1 ppm limit. So our smallest point, the smallest concentration of ethanol that we can apply is 100 ppm, but not because of the device, but because of the experimental system that we worked with. If we integrated our device inside the gas chromatographer, we would have also points that are for lower concentrations. And for detection of TNT and C4, we need to work over here at this range of ppm or below ppm concentrations, and to be selective to the specific gas of interest. Currently, nobody has done this with reliability in a micro sensor kind of setting. So now, up until now, I just described what we've done before. And the problem in here was the existence of this gap between the actuating electrode and the bridge that we worked with. So our challenges in the future are uncertainty in the residual stress, the difficulty to control the stress by the process. Stiction of the fabrication stage is still a problem because many of our devices don't even survive in the process. And stiction of the operation stage when this gap is narrow. So I don't want to get too much into the details, but we have an optimization of this gap so that the gap is small enough to minimize dissipation losses, right? But it is not too small because the electric force can just snap the bridge down to the electrode, and this is irreversible. So ice squeeze film dumping in air is kind of a big issue in here that gives us a restriction on the gap that we can work with. This is a kind of a new generation of device that we plan to apply for gas sensing that is single layer. Okay, as opposed to the previous generation that was multi-layer, we had the stack of several layers, one on top of the other. In this geometry, the electrode is coplanar with the device. And therefore, we have no problem of stiction. We can actuate the beam with as high amplitude as we want, and it will not be restricted as long as we don't exceed the range of the electric field. If we get out of the area of the electric field, the beam will just not actuate anymore, right? Because there will be no restoring force on it. So I will just skip this, and I will describe future architectures in which we plan to apply multiple polymer adsorptive layers at cantilever beams that have a single electrode, or clamped beams that are bridge types. We have two anchors over here, and two electrodes from the side. And the polymer is deposited not on the electrode, but only on the beam area and its anchors. This is pretty much a possibility to actuate several devices, let's say 100 or 200 devices from a single electrode, rather than wire bond each one of them separately. I will now briefly describe the measurement in the opposite limit that I described earlier inside liquids. We also want to make measurements inside solutions. And in solutions, the viscous dissipation is dominant. You have a very high viscous dissipation, and therefore the resolution for components is very low. So optomechanics inside the liquids is kind of a big challenge right now. In this setting, we have also used membranes instead of bridges or cantilevers that allow the water to penetrate from the sides and possibly also destroy our sensor. In membranes that are circularly clamped, the water exists only on top of the membrane and not below. So we still have an air gap existent here, even inside solution. Okay, we have applied such membranes. These are not really micromembranes, but kind of millimeter-sized membranes for gravimetric mass detection under harsh conditions. So if we start with a clean membrane and we dip it in water, we have attempted to apply droplets with a microfluidic array from beneath the chip. So this is kind of the water droplet that exists here that causes some downward frequency shift. And we have also tried to operate under very harsh conditions, harsh realistic conditions, such as a spray of ethanol. And we have managed to still get the operation of our device afterwards, even though it had to be cleaned in order to go back to its base state. So I remind you that in liquid, we have very low quality factors, and the resonances are very wide. In this case, we have a fundamental frequency of 26 kilohertz and a quality factor of 15. But still, when we apply a large dose of liquid on top of our membranes, then we get a downward frequency shift. And importantly, after drying, the response returns to its original state. This is the frequency of the central response as a function of the time. It drops initially and then goes back to its original state, meaning that the measurement is reversible. We could repeat it many times afterwards. From a calculation, we can also deduce what is the mass deposited in here. So the base mass of the membrane is 50 nanograms, and the added mass is 1.2 micrograms, which is kind of 50 times larger than the internal mass of the membrane. It still survived it, okay? The measurement. In the spray sensing setting, we have found that the frequency shift here is due to 4 splashes of spray applied from the top. So this is the first one, this is the second one, and this is the third one. Afterwards, the resonant frequency stays here indefinitely. So our device is kind of deteriorated after the measurement, right? After we clean this device, the resonant frequency will go back to its original case as long as we get rid of residuals on our device. And again, we can deduce what is the added mass in this measurement. As I said previously, in the future, what we want to do is to integrate our chips, our sensors, inside the glass chromatographer in order to have access to low concentrations. At the edge of the injection line, we plan to add an XYZ stage and make a measurement of our micro and nano sensors in parallel with the chromatographic measurement. And this will also be useful in order to calibrate our devices for a multiplex detection of more than one component in the gas. So to conclude, MEMS and NEMS resonator arrays are used to sense vapor and liquid in high and low concentrations. In the future, we will selectively measure key chemical and biological materials. In the long-term goal, we would like a product. We would like to be able to measure in real time ambient chemicals of interest with a low-cost, sensitive, selective, and fast standalone solution. So thank you very much. Yes.
Hi. Hello? Okay. You mentioned that the membranes are reversible. Are the cantilevers reversible as well? Can you return the cantilevers to a pre-buckled state after they've absorbed whatever particles?
The illustration of the cantilevers?
Right. Are they reversible? Can you return them to a pre-buckled state after they've been operated?
That is a challenge. That is a challenge, and because we've used basically fabrication kind of stresses, all buckling changes are irreversible, unless we are able to somehow wash the adsorbent layer on top. In this case, we worked with PMMA, right? So in some reactions, the diffusion of the chemical inside the coating layer is reversible. So after you flush your device in clean nitrogen, let's say for an hour, after it's been saturated in ethanol, you can take it back to the close to critical buckling state. But I will not say that this happens generally. Let's say if I use some abrasive materials, even with very low concentrations, such as hexane, let's say, even with concentrations of 100 PMMA in nitrogen, it changes the total buckling of the device irreversibly. Even after overnight, like overnight flushing, it never recovers to the original state, and that is really a challenge for this whole field, right? To have, let's say, on one chip you can make 1 million cantilevers like this, each one of them potentially with a different coating, and some of them you can sacrifice, right? The thing is that you want to not sacrifice it too often, like every day, because cheap sensors that are specific for a certain analyte that you change every day already exist, right? We want a durable operation. Yes.
Can you measure change of quality factor during adsorption or swelling? You know, if it's possible, it will give you additional dimension.
Yes, I can measure it. Usually it doesn't change.
Usually it doesn't change.
I mean, it changes linearly. It scales the same as the frequency itself.
It's frequency, yeah?
Yes.
So independently of, let's say, kind of adsorbent?
Yes, in gas settings, mostly we are dominated by squeeze film damping. So it dominates over everything. Usually, if you really want to measure changes in the quality factor, you work in vacuum. So, of course, all the devices we test first under vacuum conditions where the quality factor is high. So it can be 100,000 or 1 million, and very sensitive to small changes. So in this settings, the quality factor does change. We do measure it, but in viscous fluids settings, basically the dissipation doesn't change. It's mostly dominated by the viscous damping. So, thank you again.
Let's take the speaker again.